This is Mr. Yeager with physics. This is part 2 for momentum. So if you watched the last video, you saw that we ended with this particular slide, basically talking about how collisions are either elastic or inelastic. Again, pointing out the fact that elastic collisions are where the kinetic and momentum are both conserved, and inelastic are where only momentum is conserved. So I want to go a little more in detail about this as we move on a little bit. I'm going to probably move along pretty quickly here. Okay. So again, this was mentioned a little bit in the last video. With elastic collisions, all right, the kinetic energy must be conserved. And I said this will only occur if the objects actually bounce off of each other. Okay. Now, they're sometimes called a perfectly elastic collision. Don't worry about that word perfect at all. This is, again, a very ideal situation. It doesn't happen really in life at all because of friction pulling out some of that energy. But we can get, again, very close with the examples of, throwing a ball against a wall and having it bounce back almost as quickly, basically. All right, almost identical to it. So that would be an elastic collision. Again, another example down the bottom with the cue ball hitting an 8-ball, and it transfers all the energy to it. All right. Momentum will always be conserved, but again, the big thing is the objects have to bounce off of each other to be possibly elastic. All right. So don't sit there and go, oh, they bounce, it's elastic. Nope. Don't think of elastic as stretchy or anything else like that. It simply means that the kinetic energy will be conserved as well as the momentum. Okay. In an inelastic collision, again, kinetic energy will be lost. Okay, energy will not be conserved; it will be lost outside the system, essentially. All right. Again, as it states there, this usually will occur during a collision because some of that energy does change into thermal and sound energy or other forms. Okay, it's used to basically warp and manipulate the masses into different forms. Okay. So inelastic can occur when objects bounce, but one way you know it's definitely inelastic is when the objects couple. Again, this was talked about last time. That's when we combine the two objects. You have one car hitting another one, and then they both travel off together. They get mangled and pulled together, and they travel off as a single larger mass. All right, that will be inelastic. Sometimes they call that perfectly inelastic collision. Again, don't be pulled by that word perfect. It really doesn't mean too much. All right. So we have a little practice problem here. I'm going to go kind of back and forth a little bit. You can see it has multiple parts to it. I'm going to try to move through this as quickly as I can. Okay. So first question is, what's the initial momentum of the halfback? The halfback is running 95 kilograms. Sorry, is 95 kilograms going 4.1 meters per second. So the momentum would be simply 95 times 4.1, and that would equal 390. That's rounded. 390 Newton seconds. Again, Newton seconds is one version of the momentum unit. You could do kilograms meters per second as well. That's fine. I just like Newton seconds. It says draw the momentum vector. Again, that's mainly for us to make sure we know that which way is the object, is the halfback, the object moving. Okay. What's the initial momentum of the cornerback? The cornerback is chasing him. Is tackled. The cornerback is running 5.5 meters per second in the same direction. So the momentum is actually in the same direction. Okay? And so we do the same thing. P equals m times v. Okay, I'm using this formula. P equals mv. Momentum equals mass times velocity. And that's 85 times 5.5. And that will equal 468 Newton seconds. All right? What is the final momentum of the halfback cornerback together? So this is an example of a conservation of momentum. We are colliding. The objects do collide. Again, when we look at conservation of momentum, we're looking at what is the momentum of the objects just before colliding. That's 390 and 468. And what will be the momentum just after the collision? That's when the two objects are now together. So I'm going to go back to the whiteboard so we can see this better. All right. But basically we're saying the sum of the initial momentums must equal the sum of the final momentums. Well, initially you have two different objects. You have the halfback and the cornerback. Afterwards, they are tackled together. They are together at this particular point. Okay? So all I have to do is just add these two momentums up. So 390 plus 468 equals the final momentum of the two objects together, the two people, I should say, is 858 Newton seconds. That's it. That's all we got to do. All right? And so I think for part D, it's now saying, what is the final velocity of the two together? Okay? What is the final velocity of the two together? All right? So, now I have to split this up. Now I know the final momentum. The final momentum is 858 Newton seconds. Well, momentum equals mass times velocity. Well, what's the mass? The masses of the two objects together. 858 will equal, I have to add the two masses together, is 180 times v, solve for the velocity. Hopefully it should be smaller because obviously we're adding more mass. So this comes out to 4.8, or actually it should come out in between them, 4.8 meters per second. It should come out somewhere where they're together here, right, between the two. Obviously it's like an average almost, not really. All right, but 4.8 meters per second, okay? So that would be their final velocity together. So he's running one way, he's running after him. If I said draw this vector, they're both running the same direction, all right? Obviously, it does have a larger momentum because the two people are together, and technically they're still moving, all right? So next question, I'm going to look at this real quick. E and F, asking for the initial and final kinetic energy because we want to know whether the collision will be elastic or inelastic. We know momentum will be conserved, but will kinetic energy. The only way to ever figure that out is you have to calculate them out. So, the initial kinetic energy, I simply just add the two together. So it would be 1/2 times, I think 85, sorry, 95 times 4.1. 95 times 4.1 squared plus 1/2 times 85 times, I think it's going 5.5, yep, 5.5, 5.5 squared. We got to add up the total kinetic energy before the collision. That comes out to 2084.1 joules. Let's figure out the total kinetic energy after the collision. After the collision, they are together. So the total mass all moving together is 180 kilograms times going, what is it, 4.8 meters per second. 4.8 meters per second. Square that. It actually comes out pretty stinking close. Usually it won't come out this close. Most of the time, a lot more energy is lost. But the thing is, are these exactly the same? No, they are not exactly the same. This would be something that would be relatively close. Some people might say, hey, it's within actually 1%. So it could almost be elastic, but for this particular problem, we're going to call this inelastic. We're going to be very specific with this one. Sometimes with it, if it's within the 1%, we're going, who cares? It's fine. 1% energy loss is really not that big of a deal. All right? But we're going to say this one is inelastic, definitely. All right? So that's how you approach these problems. You can see we did just simple momentum calculations. We used the conservation of momentum, momentum before, momentum after the collision. We're able to find the velocity, compare kinetic energies before and after, and determine whether it is elastic or inelastic. Okay? So that leads us now to the graphs. Okay? There are a lot of graphs that we could make that help us interpret impulse and momentum. And the first one is the force time graph. Okay? If you see a force time, and again, you got to be careful because you've seen a force distance graph. Okay? We've seen force acceleration graphs. There's all different types with force. This is force and time. Okay? So make sure you pay attention. Also, make sure you pay attention to the time units. There's going to be a lot of times where it's only going to be milliseconds, so you're going to have to convert before you solve. But, as always with the graph, you're interested in either the slope or the area. So you sit here and go, slope, force divided by time. That means nothing. So the slope is worthless. The area is force times time. Hey, I know what that is. That is impulse. All right? That is impulse. Obviously, it's also possibly the change in momentum. So very, very common to get a force-time graph and have you solve for impulse, which then could make you try to solve for velocity if you know the mass of the object. It could ask you what's the change in velocity. So we would just solve for the area underneath the lines. Again, be aware that you can have positive or negative impulses. Okay, that's the direction that the impulse is being applied. Okay, so force-time graph, area, impulse. All right, I think we have a practice one here. It says find the impulse of this particular graph. Let's try to do this pretty quickly here. I would make a triangle and a rectangle. Okay? And this would be 1/2 times 4 is the base, times 4 is the height. That would give me 8 Newton seconds. So the impulse is 8 Newton seconds. Just combine the two. Over here, this would be 4 times 1, so 4 Newton seconds. So the total impulse occurring is 12 Newton seconds. What's the change in momentum? 12 Newton seconds. They are equal to each other. That is the most common connection in a multiple choice problem. They'll give you this graph, but then we're going to be more interested in the change in momentum, not the impulse. So here we go. Here's a good example. If the object was 10 kilograms and initially moving 2 meters per second, what is the final velocity of the object? So what am I supposed to do here? It's change in momentum equals final momentum minus initial momentum. But I'm trying to find the final velocity, so I can split this up. Okay? I'm going to go ahead and just keep on going right here. So I know the change in momentum is 12. That'll equal, this is mass times final velocity minus mass times initial velocity, V naught. Okay? So I can pull the 2 out, or the m out. So 10 is the mass times Vf minus 2. All right? So how do I figure this out? Divide 1.2 equals Vf minus 2. The final velocity of this object will be 3.2 meters per second. This is the math you'd be prepared for in the AP test. They don't look for anything too complicated. It's something that should be able to be done in your head. So the final velocity is 3.2. What's the final momentum? Let's just go back. 10 times 3.2 equals 32 Newton seconds. Okay? Part C and Part D would be the more common question using this graph on a multiple choice test, even on pre-response. Okay, they want you to carry it beyond simply just finding the area. All right. On a momentum time graph, this is another version. Okay. If they have momentum on the y-axis, this will give you force as the slope. Again, if we think about it, I'll just leave it right here. Change in momentum equals force times time. I can divide time out. Momentum divided by time equals the force. So this is another possibility where, hey, not the area this time, not the area, okay, the slope, all right, if I just write this as y equals m times x, you can see slope will equal the force, okay, on the graph. All right, so that's it. Graphs should be, are always, we're hoping, will be easy questions because it's the same thing we're going to be looking at every single time, slope, area, just figuring out what quantity does it equal to. All right, so find the net force in all the regions here. All right, I'll try to be a little quick here. Find the net force in all of the regions. All right, so right here, we are going up 4 in 4 seconds, so the net force here is 1 Newton. Okay, or the average force is 1 Newton. During this time, it's a 0 slope, so 0 Newtons. It still has momentum, but it's not changing anymore. If there's no force being applied, time can keep on moving, but the momentum does not change. This one's going back down, so this would be 1/2 times 2 times going down 8. So this would be, and we have to go going down -8. This would be -8 Newton seconds, and then D would be again 0. 0 Newton seconds. Okay. If the object had a mass of 2 kilograms, what is the final velocity of the object at 4 seconds? So we're just looking at the beginning. Okay. If the object had a mass of 2 kilograms, what is the final velocity of the object at 4 seconds? Okay. Now this one, not trying to be a little confusing or anything, we can sort of figure this out just by going back and looking at momentum here. Okay. If I look at it at 4 seconds, what is the momentum of the object? The momentum of the object is 8. So really, this question is a little bit more tricky because you might be thinking you have to use the slope and everything, but all you're doing is going, hey, the momentum is 8 at 4 seconds, and so therefore, if the object is 2 kilograms, what's the velocity? Velocity will be 4 meters per second. Okay. So a little tricky there, kind of going to a side where sometimes you don't have to use slope or area to solve the problem. It's just, hey, this is momentum, what's going on here, okay? So be a little careful with that. That one's a little bit tricky. All right, collisions at an angle, all right? They really try not to overcomplicate this. This is going to be much more of, again, a conceptually bound question rather than calculating a lot of pieces out. The main thing to realize is, in order to think about, is momentum will be conserved in all directions. Momentum must be conserved in all directions. And that's what this is saying right here. At an angle, the sum of the initial x momentums, the horizontal momentums, must equal the final horizontal momentums. The sum of the initial y momentums must equal the sum of the final y momentums. Okay? We do have to treat them separately, just like when we did with projectiles. But before you start freaking out about this, all right? Again, you will not. It is highly, highly unlikely. I haven't seen one yet in any of the years they've done AP Physics 1, where you're going to have to complete the entire 2D problem or calculate everything. All they're really going to ask is, or things that you have to realize and think about, is will momentum be conserved in the x direction? Answer to that, yes. Momentum's always conserved. Is momentum conserved in the y direction? Yes. Momentum's always conserved. Okay? And so what might happen is they might give you a little scenario to say, all right, you see these objects move, what should happen afterwards? Well, if you see an object now moving downward, we'll go back to it in a second with the cue ball, we must be able to have everything cancel out appropriately. If there was no momentum in the y direction initially, and there is some afterwards, there must be something that counterbalances that and pushes it in the opposite direction. Okay? Which object will have a greater y momentum and a y velocity? Okay? That will, again, maybe occur depending on the masses of the objects. Okay? Maybe they're two different masses. And same thing goes with in the x momentum. It depends on the objects themselves, if we have to pay attention to mass. Okay? They might have the same momentum because they might cancel each other out, but they might have different velocities. All right? So if we go back to this particular problem, okay, the cue ball is 0.5 kilograms, 8 ball is 1 kilogram. Okay, so we have two different masses. You can see what's happening here. The cue ball comes in, the 8 ball is at rest. The 8 ball initially starts at rest. So the only thing with momentum at the beginning is the cue ball. Then the cue ball, when it strikes, gets hit at an angle downwards. It still has a x and y component, same with the 8 ball. Okay? But this is what we're trying to figure out. What would have greater velocity possibly and so forth. So let's look at this. Which ball has the greater magnitude of momentum in the y direction after the collision? Well, let's think about it. All right. What is the initial y momentum of this cue ball? The initial y momentum of the cue ball is 0. So the total final y momentum has to come out to 0, which means, what can you tell me about the py of the 8 ball and the py of the cue ball? They must be equal and opposite. They're going to be equal to each other. All right? Doesn't mean that one's moving, like cue ball's probably moving faster. It has to be actually in the y direction because it's lighter in order to have equal momentums, but they are equal to each other. They're equal and opposite. They're going to cancel each other out. Which ball has a greater velocity in the y direction? I just said the cue ball. Y, less mass. Momentum is equal to mass times velocity. If the momentums are the same and the mass is less, that means the velocity has to be more. Will momentum be conserved in the x direction? Yes, 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 yes. If there's no friction, which there basically never is, it will be conserved. Okay? These are all things that, again, believe in yourself. Yes, it will be conserved. All right? Now, it doesn't go into any more information. That's all I want to know. But yes, it will be conserved in the x direction. Okay? So last thing to cover with this, which comes up quite a bit with momentum. Okay? Again, like you see, just so you know. Okay? You will see problems that talk about the momentum of the center of mass. All right? After two cars collide and so forth. Okay? You'll see actually other problems where it might be a rocket and it jettisons part of the rocket off of it and says what happens to the center of mass. They talk about the center of mass because it's the center of mass that is officially following Newton's second law. Okay, during a collision, in a system. Okay, the center of mass is what's following the second law. Okay, so that is what we are thinking about in terms of it's continuing its motion. All right, why it will move in a particular direction versus another one. Okay, why a larger car will obviously push a smaller car backwards and everything like that. It has to do with the center of mass, and that's what's moving. Okay, so what you need to know really about center of mass is, again, some very simple conceptual type things. Okay, the center of mass is, there is a formula, you'll see it on the next page, is basically a weighted average. Where is the mass in comparison to all the objects in the system? Okay, if the masses are equal to each other, the center of mass is right in the middle of them. Okay, that's what we say. If the two objects are equal distance apart, think of two objects connected to a rope. If they're equal to each other, the center of mass is right in the middle. Okay. If the masses are unequal, the center of mass will always be closer to the heavier object. Okay. Most times, you can ignore that it's talking about center of mass. It is, sometimes they just talk about it, and you're going, what am I reading here? It's pointless. You don't even need to worry about it. But if you do want to worry about it all, basically 1 and 2 are telling you all you really need to think about what the center of mass is doing. Where is it compared to the two objects? All right. This is the official equation for it. Okay. Center of mass is the XCM right here. All right. It will be multiplied by the total masses of the system. It can be found by basically calculating the mass of each object and where it is in the system. Okay. The thing is, if you have two objects, object 1 and object 2, all right, and they are, let's say, 10 centimeters apart. This is basically comparable to the problem on the next page. If they're 10 centimeters apart, we would label one of these objects as at x equals 0. And so then all you would do is just basically go, what's the mass of 2 times 10? And then equal that out to m1 plus m2 and solve for xcm, center of mass, the distance. Where is the center of mass? All right. So it's, again, very relative. You have to kind of pick out what is the 0 point. Go ahead and do that. Usually set it up at one side and then measure everything from that particular point. It eliminates one of these calculations. All right. So really, for the rest of this, I'm going to put up the answers for it. All right. If you want to calculate it, it's fine. Basically, I'll make sure that you understand what you're doing with it. All right. The center of mass between these objects is at 5 centimeters. The center of mass between these two unequal massed objects is 6.7 centimeters. On this last page, where you have the sun and the moon, or sun and moon, sun and the earth, sun, earth, okay? Now, I'll tell you this, I set the sun at x equals 0. And when I solve this, again, if you set the earth at x equals 0, you'll get a much larger distance. It'll basically be on the other side of it. But we know the center of mass should be closer to the sun. It's much more massive than the earth. All right, so I set that at 0. I have the center of mass being found at 4.5 times 10 to the 5th meters. Okay, 4.5 times 10 to the 5th meters. All right. And that's it. Okay, based on the numbers given in the problem. If you do solve for it from, again, that's measuring from here out. If you take this as x equals 0, you should hopefully have a much larger answer where it's showing you that the center of mass is much closer to the sun. Okay, so that is it. Thank you very much.